Imagine you spent months training a language model, and now the team want a bigger one. The usual answer is brutal. You throw the old weights away and train the whole thing again from scratch, burning an enormous compute bill. But what if a model could simply grow instead? That is the bet behind TokenFormer, a paper out of the Max Planck Institute, Google, and Peking University. It treats the model's own parameters as tokens, so scaling up becomes as gentle as adding a few more. Let us unpack how that actually works. Look, the whole idea rests on one repeated building block. Input tokens flow in on the left, attend to the model's parameters in the middle, and leave as richer tokens on the right. Follow the path one stage at a time. Everything starts with the input tokens. In a normal transformer, these would be hit by a fixed linear projection, a rigid weight matrix baked into the layer. TokenFormer instead lets each input token act as a query, asking a question of the model's parameters rather than being multiplied by a frozen sheet of numbers. Here the parameters themselves become tokens. TokenFormer stores each weight as a learnable key token, so the network holds a whole pool of parameter keys the queries can attend to. This is the heart of what the authors call patention, token to parameter attention, where the weights are no longer a fixed matrix at all. Paired with every key sits a value token. Once the input queries score against the parameter keys, those scores weight the matching value tokens. The authors swap the usual softmax for a GULU-based normalization, which they report improves gradient stability while blending the parameter values back into each token. Finally, the blended result leaves as an output token. The dimensions coming out match the dimensions going in, and that is the quiet trick. Because the parameters are just more tokens, we can append new key value pairs without changing those input or output shapes, and every block in the stack repeats this exact same pattern. So, why does treating parameters as tokens matter so much? Put the old way and the new way right beside each other. A standard transformer bakes its parameter count into fixed linear layers. Widen the model and those weight matrices change shape, so the old checkpoint no longer fits inside the new network. That forces you to restart training from scratch, paying the full compute bill every single time you want a larger model. It is expensive and genuinely wasteful. TokenFormer keeps the same attention machinery and simply grows its pool of parameter tokens. To scale up, you append fresh key value token pairs and reuse the smaller model's learned weights as a warm starting point. The team scaled one model from 124 million all the way to 1.4 billion parameters this way, reporting a substantially lower cumulative training budget than training each size alone. Strip it back, and 3 ideas make TokenFormer worth knowing. Parameters are treated as tokens. Rather than fixed weight matrices, TokenFormer stores parameters as learnable key and value tokens, and its patention layer lets input tokens attend to them exactly like they attend to each other. One attention primitive now handles both token to token and token to parameter interaction. Models grow without full retraining. Because scaling just means adding more parameter tokens, you can start from a trained smaller network and expand it incrementally. The authors progressively scaled through 354 million and 757 million on the way to 1.4 billion, reusing earlier weights instead of restarting each run from zero. A single design spans modalities. Trained on 300 billion tokens from a pile, TokenFormer reaches competitive zero-shot language performance, and the same architecture matches a vision transformer on ImageNet classification. That flexibility comes almost for free from making everything, both data and weights, into tokens. All right, let's lock in what matters. TokenFormer is a fully attention-based architecture that treats the model's own parameters as tokens, replacing fixed linear projections with a token-to-parameter attention layer the authors call pattention. Input tokens act as queries that attend to learnable parameter key and value tokens. Using a GULU-based normalization, the paper reports improves gradient stability over the plain softmax. Because parameters are just tokens, the network scales by appending new pairs, growing from 124 million to 1.4 billion parameters while reusing earlier weights and cutting the cumulative training budget. Coming from the Max Planck Institute, Google, and Peking University in 2024, it hints at models that grow rather than restart. Want more AI research made clear without the hype? Come explore it with us over at standarity.com.